Hi there and welcome to this lecture in solar cells. In this lecture we will be discussing printable solar cells based on organic material. Regular solar cells is usually made out of silicon, which is a semiconductor material that has quite a high cost. If you instead use organic materials, you can print such solar cells on flexible substrates such as plastics and even paper. Such solar cells can be manufactured with printing technology over very large areas to a low cost. This, however, is developing each year and the efficiency increases rapidly. In the foreseeable future, it is quite possible that such printed solar cells completely can replace the standard silicon solar cells, giving the possibility of cheap energy. Welcome to this lecture about solar cells. The suggested literature for this lecture is Chapter 6, Imprinting Technology for Flexible Substrates. Solar cells, also called photovoltaics, is two terminal devices that convert light into electrical energy. The semiconductor material absorbs the incident light and creates a charge pair. The charges are then separated by an electrical field and is extracted from the contacts connected to the equipment powered by the cell. Usually the voltage generated is somewhere between 0.5 and 1 volt, and the current can be some tens of milliamperes per square centimeter of solar cells. This depends on the type of semiconductor material used. For a higher voltage, the cells are connected in series, and for a higher current in parallel. Some different classes of solar cells is the silicon semiconductor, the compound semiconductor, the organic semiconductor, and metal oxide semiconductor types, also called dye-sensitized. In this lecture, the focus will be on organic semiconductor cells, the most commonly used material for printing on flexible substrates. Silicon solar cells is the most commonly used type of solar cell today. Some background information about the silicon cell. The first silicon-based solar cell was developed in 1954. They can be produced out of three types of silicon material: crystalline, polycrystalline or amorphous. The crystalline silicon solar cell have the highest efficiency, but are also the most expensive to manufacture. Polycrystalline SC cells is cheaper but have a lower efficiency. The cheapest type is the amorphous silicon cell. It is the cheapest to manufacture but also has the lowest efficiency. Here is displayed some solar cell efficiencies. As you can see, the organic cells has pretty low efficiency. However, this is increasing basically every year as development of these types of cell is going forward. I will here show the typical operation of an organic semiconductor solar cell. When the light is incident on the organic material, the molecules absorb the light and electrons is excited to the lowest unoccupied molecular orbital and leave holes in the highest occupied molecular orbital, forming an exciton. One electrode is transparent and have a high work function. Typically this can be indium tin oxide. The other electrode have a low work function, and typically this can be aluminum. This sets up an electric field that separates the electrons and holes and transport them to the electrodes where they can be extracted and form a current. The exciton is a quasi-particle consisting of an electron in the conduction band bound together with a hole in the valence band. The exciton moves as a unit and has zero net charge but transports energy. The amount of current that is generated by a solar cell can be described by the external quantum efficiency of the device. The external quantum efficiency is the efficiency given as the number of charge pair extracted per incident photon that is absorbed, and the maximum is 1 charge per photon. A good way to write the external quantum efficiency is as a product of factors corresponding to each of the processes involved in photon to electron conversion. Examining this equation, the different processes involved in photon to electron conversion is the following: the efficiency of charge separation and the charge collection. Note that these are responsible for the voltage dependence of the photocurrent. Then we have the absorption, the exciton harvesting, and the charge transfer. And these factors are considered voltage independent. The polaron is a quasi-particle composed of a charged particle and an accompanying polarization field moving through a polarizable medium. The figure shows an electron moving in a crystal and attracting repelling positive and negative ions. This entity is called a polaron. To find out the photocurrent produced by the solar cell, we need to look at the number of charge carriers produced. And the number of charge carriers produced by a solar cell is found by integrating the incident solar flux multiplied with the external quantum efficiency over the spectrum of interest. The spectrum of interest in this case is most likely the outdoor solar spectrum, but it could of course be something else. Then the electron charge is multiplied with this number to get the total photocurrent. And the most relevant spectrum to use for outdoor applications is the AM 1.5G solar spectrum. If integrating over all wavelengths, this will give an incident power of 1000 watts per square meter. The fill factor. An often used figure of merit is the fill factor, which is the largest power value along the measured IV curve, where the current I multiplied with the voltage V gives the largest value. Here ISC is the short circuit current, the current at zero bias. VOC is the open circuit voltage, the voltage when the current is zero and no load is applied. And Pmax is the maximum power along the measured IV curve. In an ideal solar cell, the voltage stays constant regardless of the current output until it abruptly drops to zero. In a real solar cell, the voltage drop is gradual, meaning that the total power that can be delivered is lower at a high current load. Organic solar cells show a strong voltage dependence of the photocurrent, much more so than an inorganic cell. In the example below, we have plotted an ideal and an actual photocurrent in an IV curve. If we then take the point where IV is the largest, and under that we draw the fill factor box, then the square under the IV curve represents power. Some important characteristics of organic solar cells. There need to be a strong driving force to break up the photogenerated excitons. This means that absorbed light does not necessarily add to the photocurrent. The light absorption coefficient for organic materials is high, meaning that a large amount of light is absorbed even in thin layers. The low charge carrier mobility limits the useful thickness of the device. Limited wavelength sensitivity over the solar spectrum limit the photocurrent. Mostly organic semiconductor material is sensitive to the blue-green light. We will now look at some organic solar cell device types. There are several different structures of organic type solar cells, where the simplest is the single layer structure. More advanced types are the multi-layer, where N and P type semiconductor materials is stacked. An interesting type is the blend type, where a thin active layer is formed by dispersing the organic semiconductor in a polymer matrix. In the blend case, a large number of p-n junctions is formed at the boundaries of the two materials. The homojunction device has the simplest structure and consists of a single layer of organic material between the anode and cathode. When the incident light generates an exciton, the electric field is seldom sufficient to break it up, and therefore it diffuses until it reaches a contact where it may be broken up into an electron and a hole, or it could also recombine. The charge carrier then migrates to the anode and cathode and is there collected, adding to the photocurrent. Considering that the exciton diffusion length is short, this will limit the charge carrier generation in a single layer device. This means that the photocurrent is not only depending on the optical absorption of the incoming photons, but also on an efficient breakup of the formed excitons. Losses also occur because of recombination at the interfaces and recombination at impurities or trapped charges. The quantum efficiency of single-layer solar cells is typically less than 1%. The heterojunction device consists of one layer of electron donor and one layer of electron acceptor organic material between contacts. If light is incident on the device and create an exciton, it is then energetically favorable for an exciton that reaches the interface to dissociate into charge carriers that are then separated by the electric field and transported to the anode and cathode. Dispersed heterojunction device. A more efficient design is the dispersed heterojunction device, where an electron accepting and an electron donating material is mixed together, forming a blend of the two materials. If the size of the different material domains is in the same size as the diffusion length for excitons, then there is a great chance that excitons generated anywhere in the material can diffuse to an interface and there break up into charge carriers. If a continuous path exists from each material out to the metallic contacts, the separated charge carriers may travel to the contacts and deliver a photocurrent. Some production considerations of organic solar cells. High conductivity, light transmissivity, and impermeability to oxygen and water are requirements on the substrate and contact material. The most widely used material is ethos-coated PET. It is also used for flexible amorphous silicon solar cells and has a transmissivity of light of about 80 to 90%. A relatively high resistance of 10 to 50 ohms square lead to serious resistance limitations. New organic transparent conductive coatings are studied, but no one can yet compete with ITO. A major problem is to be able to achieve a uniform film with a thickness variation within 10 nanometers over several hundred square centimeters.